Welcome back to this third and final part of the training, Transforming Earth Observation Data into Building Infrastructure Data Sets for Disaster Risk Modeling. My name is Brock Blevins, and I'm your host for today's session. Just to quickly catch us up to speed, why is climate and disaster risk assessment important? So even with drastic reduction in carbon emissions, short and medium-term impacts are inevitable. Climate change impacts and risks are becoming increasingly complex and more difficult to manage. Climate change impacts on human infrastructure are not well understood and vary drastically by location. So understanding community-specific risks to climate change is critical to evaluating adaptation strategies. And just to remind us a little bit of our journey here, in the past week, we've gone through parts 1 and 2 on developing regional exposure data, developing site-specific exposure data with Earth observations. So today in the final part, we're going to discuss assessing utility and communicating uncertainty. Once again, there's one homework associated with this training. It is now open today. It is on the training webpage, and it will be due 2 weeks from now, so October 24th. These are Google form submissions. So let's move right into part 3. By the end of today, we aim that participants will be able to evaluate the appropriate use of modeled building exposure data to a given community, to apply strategies to identify and address equity and bias considerations, apply approaches to validate building data and imagery from regional data sets, and then to document your exposure development process through metadata so that others can understand the process used, the limitations, and how to update if necessary. Our trainers today will be Charlie Hike, Executive Vice President of ImageCat. We also have Marina Mendoza, Paul Amix, and Mike Giguchi, all also from ImageCat. So we'll start off with Mike today on how to check exposure data and ensure that it is fit for purpose. Thank you, Mike.
Hi, I'm Mike Giguchi, and today I'll be going over how to check your exposure data and ensure that it's fit for your purpose. So here's a quick summary on the objectives of this presentation. First, we'll just go through an overview of the different levels, the 1 through 5 levels, the background data behind it. Second, we'll go through any pre-event uses. Basically, how can each level assist in mitigation strategies? Can it help with further building code development or any risk management strategies? Are there any implications to the reinsurance and insurance industries? We'll go through any post-event uses. Basically, how can these be used for anything like a post-disaster response? And finally, we'll go through some of the limitations. What are the limitations in the data? How should the data not be used, etc. So first, we have level 1 global data. It relies on the best available data global sets. If you're looking for very high-level building distributions, this is something you would use. Something along the lines of Pager. Country-specific information can be very limited. If a number of buildings or square footage are provided, they're most likely inferred from a few additional attributes, such as a number of people per household. These mapping schemes or structural distributions by a building type may be estimates gleaned from the World Housing Survey or any other journal or any other resource for a given country. Oftentimes there's not enough information, so neighboring countries are used as a proxy. And these are often broken down by urban and rural regions, such as the case with Pager or some census data. These may not include square footage information or replacement costs, as the general purpose of this is to evaluate the population at risk. So how can level 1 global data sets be used for mitigation and preparation? Reminder, this is a global data set, so they should be broad-scale prioritizations for further studies. You might look at SDG framework, international research prioritizations. These SDGs and SYNDIC frameworks mandate each country to look at risks, so they should be able to look at a global scale to determine where that's more important and where there should be priority amongst NGOs to look at. Anticipatory actions, we know where the high risk places are and we know where people are located. So where should we be pre-staging our resources and where should we prioritize? In regards to insurance or reinsurance industries, they might want to look at risk diversification, or all their eggs in one basket, or do their portfolios need to be more geographically diverse? They may also be concerned with ESG. We'll get a handle on their risk for climate change. So if a large event happens, how can this level one global exposure help with the post-disaster response? So Paige, you're on the top right here. It's kind of the poster child for this type of response. It's a very rapid assessment and can help determine whether, any of the pre-event anticipatory actions from the previous slide should be implemented. If it's a large enough event, it's global one data, can't tell you whether to send anyone to a specific building or even a region, but it can help you decide whether to deploy a team. Will an international rescue team be required? Does something like Paige estimate large enough fatalities from their analysis? And because of that, will that help trigger any decisions for these post-disaster responses? So some limitations for the level one global database. It's important to remember that, this is a very high level exposure data. You're not going to start looking at country specific, region specific, or building specific types of analyses. The metadata inaccuracy will vary based on the underlying source, so be sure to know what the source is and how reliable it is for your analysis. A lot of times that there's proxy countries that are used, so just because there's country-specific data, it actually might just be used from the neighboring data since they didn't have any. What they're generally trying to do in this global data set is, capture residential development. Where do people live? What kind of general building stock is there? So it's important to remember not to use this for any region or building specific reconnaissance post-event and pre-event. At level 2, we're looking at the country level exposure. This exposure data has been collected and reviewed at the country level with structural building type distributions and other key figures such as number of people per household, building replacement cost per square footage. All this is adjusted with country specific data where possible. This data is reviewed and validated at the national level. A good example of this is the U.S. government's loss modeling software from FEMA called HAZUS. This kind of data, users receive this countrywide default data and tailor it with assumptions for their area of interest. This data may contain adjustments for local regions, but these adjustments are made at the national scale. So, for example, there may be an adjustment to estimates of people per household or building area or replacement costs for various regions of within the country, but these improved estimates are most likely gleaned from census data or other national data sets. Okay. So here are a few mitigation and preparation examples for a level 2 exposure database. It's important to remember, this is high level, national level, annualized loss estimates given the source and accuracy of the underlying data. If we start looking at, risk assessment frameworks, given what we know at the country level about our building stock and population exposed, how should we start preparing for any future large events? Could we start looking at countrywide hazard scenarios to get a rough estimate of cost and population exposed? So introduce legislation for hazard preparedness. Where and how should we start looking or focusing our efforts? Do we need any hazard mitigation plans in this country? Training and education. So, how do we educate the population on possible life safety issues post-event? How do we start training first responders for any of these post-disaster needs? And finally, we can start looking at SDG and Sendai framework compliance since we're at the country-specific level. So what do we do with level 2 exposure data for post-disaster response? The big one would be disaster declaration. We know a major event has hit the country. There's general idea of the built-up region and the population exposed. So at this point, it's whether or not a deployment of federal resources will be called. Another one would be, parametric triggered insurance. Usually this is a national level program. So if a large event occurs, there's going to be a big payout. So insurers have programs with sovereign nations to ensure that parametric insurance uses. For this, they need to do a risk assessment. Well, here's one of the big limitations of level 2 exposable databases. Basically, it accounts for no variations in regional building exposure. Remember that this is a national level database, so you're going to have maybe some small variations in building type, population exposed, replacement cost. But what doesn't take into account are these regional variations. There's just a map of the U.S. The hazard in Florida is much different than the hazard in Chicago, which is much different than the hazard in the West Coast. So based on these hazards, there's going to be variations in building. There's going to be seismic design in California, but you're not going to get that type of design in Florida, which is designed in for a hurricane. So we don't have these region-specific building mapping schemes at a national level. Yep. So now we have the level 3 exposure data. This is a data improvement, pretty much sub-national scale. What we're doing here is we're looking at those different development patterns, which we talked about previously. And what these development patterns do is they take into account region country specific mapping schemes. So, we look at any literature review, the satellite imagery, we do ground imagery just to get a sense of the built up environment. What this is able to accomplish is on this picture on the right, you see the different colors. So the red, we have an urban and the outskirts, and that turquoise are rural regions. Each of those are going to have those unique development patterns. So the distribution of the building types, number of stories, etc., are going to be much different from region to region, from development pattern. This basically makes it a enhanced building attribute database. It's only as good as the underlying data, but it's much finer resolution than national scale. So level 4 is aggregated building specific data. It's kind of similar in level 3 in that it uses pretty much a distribution or a mapping scheme type of methodology. But this level 4 data is based on site specific data, such as building footprints or tax assessor data. But then it's aggregated up, to properly represent the diversity of assets within that small region. This building specific data is often available in a municipality or somewhere as a detailed building footprint database, or maybe there's OSM data, or there's a geocoded tax assessor data. But in these cases, the data, it's typically not collected for the purpose of risk assessment, and you need to make a decision as to whether you go forward using this as site-specific data, or you want to aggregate up to a polygon or to a grid cell like the one shown here. A lot of times you can have blanks, and depending on your analysis, you might have to start filling in those blanks. So for example, if you have a seismic study you want to do, but all you have is height, occupancy, and age, you're going to have to start making some assumptions, based on the height, what year built it was, and, what the possible structural type can be. So the reason for this level 4 is basically we want to aggregate up the site-specific data just to avoid any false precision on our part. So since level 3 and level 4 are both similar in the sense that they both use distributions of the characteristics of the built-up environment, we combine the use cases here for mitigation and preparedness. Assess building stock and infrastructure at a localized level. This is pretty straightforward with the level 3 exposure. We do our research, we find what the unique building types are, we create the development patterns, and for each development pattern, there's a different distribution of those building types or mapping schemes. So here we can start looking to see where the building stock and what building stock it is based on the color. For level 4, it's a little different. It's the site-specific data. We might have things like year built, number of stories, building size. So we'll have those distributions for each of the cells. But we can also do make some assumptions given those. So if we know the height of the stories, maybe we start making some assumptions regarding structural types. Examine equity concerns. These development patterns, remember, There may be some where there's informal developments or low-income housing. So if we know where those are in this region, we can start specifying where to start looking. If that type of information isn't available for level 4 exposure data, we might rely on something such as, people per household. If we know there's a high distribution of high people per household, we might start seeing some equity concerns there. Buyout programs or mitigation programs. After level 3, we have the distributions. We might start looking at where there's a high distribution of these really vulnerable buildings, such as the URM or unreinforced masonry buildings. For level 4, it might be a little different. If we don't have that actual structure data and it's just assumed, so we can start looking at, really old, maybe pre-code buildings where those are high distribution within the region. Scenarios for hazard planning for level 3 and 4. Level 3, maybe we have the good structural data to run a scenario and see, estimated damages across the region. Level 4, we also have the assumptions for structural type, but maybe we also have such things as, the exposed population. So we can start looking there as well. Local hazard mitigation plans, combining all this stuff together. We know the structural types, distributions for level 3, level 4, maybe it's more of a population issue or other things. We can start creation of these local hazard mitigation plans. So level 3 and 4 exposure, we do post-event. So if we look at the first 2, search and rescue missions, which region to focus on building reconnaissance. Level 3 data, we know where the highly vulnerable percentage of buildings are. Start looking there. Level 4 data, if structural assumptions are made based on the existing site-specific data, we can start looking for those bad actors too. Perhaps level 4 data has population data as well in it. So we look at those regions where, large populations exposed, where to allocate personal equipment, and where emergency shelters and aids should be focused. Kind of opposite of the first 2 points, we know where the bad actors are. Bad actors in regards to building vulnerability. Perhaps we start looking at, new construction, less vulnerable buildings. And that's where you could start setting up, any of these emergency shelters, just because you need the built environment. Maybe it handled the event much better. Coordination, collaboration, and mutual aid. We know we probably have estimates of building damage for level 3 data, level 4 data. If the data is there, we have population exposed, so we can see we can kind of estimate the efforts required for any of these collaboration, mutual aid efforts. So what are the limitations of level 3 or level 4 exposure data? Although you have a better understanding of the built environment, the research is done, the types of buildings, you have a pretty good estimate of the building distribution or mapping schemes for exposure 3, or perhaps level 4 census data is very good. You still can use these for site-specific analyses or individual building tagging. So, for example, if an earthquake happened and you wanted else to be red tagged, you need an engineer to do that after a site visit. Caveat, with good quality level point data and level 4 analyses, building-specific data can be used to identify key facilities for future studies, talking about schools, hospitals, any kind of emergency operations. With that good quality point data, perhaps there's accurate geocoding, accurate year builds, accurate stories, perhaps structural types or inferred structural types to use. You can get a general overview of risk. Level 4, you do have that loss of geographic precision. So you're going from the site level up to this gridded level. So that's where your loss of geographic precision is occurring. So level 5 is similar to level 4 in that it's site-specific data, but here you're running it at the building level, and you're not aggregating it up as we level 4, creating these mapping schemes. It's optimal when you have enough data to make an assessment at the site-specific location. The advantage here for level 5 is that when you need site-level precision, such as the case of floods, surface fault rupture, landslides, or tsunami, you have that location and you don't lose it when you aggregate it up. So what can we do with level 5 exposure data in regards to mitigation and preparedness? Since we don't lose the geographic precision of our building data, we can start looking at some site-specific hazards. Is it in a flood zone, landslide zone, surface fault rupture zone? We know since we have the location essentially of these facilities. In prioritize engineering review, we think we have some vulnerable buildings here based on construction year built. Let's have a further look. All these still will depend on the appropriateness and the source of the underlying data. Life safety essential facilities. Let's have a look and can they perform to the necessary levels at post-event. Buyout and manage retreat. Do we have bad actors in this area that need a buyout or perhaps demolition? Manage retreat. Are these in high hazard zones such as the coastal regions? And finally, retrofit or mitigation strategies. Like where should we be spending our money based on what we know at site-specific levels? So for post-event level 5 exposure data, we start looking at things like site review and safety, restoration and business operations. These decisions can be made based on the quality of the information that's underlying the level 5 exposure data. Basically, you want to ask, where to send the building officials and engineers to make sure that things are okay, how to manage the recovery, where outside of the impacted area is enough that we can dependably start sending supplies or emergency vehicles. Restoration of business operations. For example, if you have a portfolio of commercial properties, we can start looking at hazard intensities at each geographic location, vulnerabilities of these existing buildings, and start prioritizing where to perhaps close or open certain business for the site is reviewed by the engineer. The biggest limitations of level 5 is that the building characteristics are only as accurate as the source provided. Basically, it's really important to understand where or who does the base data come from before you do any of the analysis. For example, if it's an insurance portfolio, maybe they're only interested in number of stories and ISO codes, so you don't get that structural information that you really need, and you're going to have to start mapping those. If it's an engineering portfolio, it's going to be pretty accurate in regards to number of stories year built, a lot of force resistant systems. So any kind of seismic risk assessment is going to be good for that. Perhaps it's a field survey. If field team goes out, records anything that they can see. It's engineers on the field, maybe they're reporting any structural issues as well. So level 5, it's important to understand basically where this base data comes from. It's going to determine how you're going to use the level 5 exposure data. So here's just an overview of everything we went through. Columns 1, 2, 3, 4, 5 are just exposure levels. On our left, we have building code mitigation, post-disaster response, insurance, reinsurance uses. The last column is the engineering review. And then for each slide, we said, you can't make any site-specific assumptions. So this is where this would come into play. The engineer goes out, reviews, it's post-disaster, they'll look at any damage. It's pre-disaster, they'll look at maybe a site visit, review any structural drawings, see any vulnerabilities, possibly run a PML or AAL, basically. So when you want to go site-specific, this is the kind of stuff you should do. Okay. So a few last thoughts on the 1 through 5 exposure database. First, assess the needs and levels of effort required for analysis. You don't want to start going into site-specific details if it's going to be a global exposure database. Each level has your own advantage and disadvantage that should be acknowledged by the user. So data may be precise from an engineer standpoint, but inaccurate from a replacement cost standpoint, or vice versa. So these levels should be used only to communicate the high-level approach used to develop the data. Important, understand the source and collection of data. Basically, who collected and how reliable can it conservatively be? If you're doing a seismic study and you have a portfolio from an engineering firm, you can assume it's probably quite a bit better from any text assessor data or such. And never make building-specific decisions or assessments such as red tagging. These pre- and post-assessments need to be performed by the engineer on field, so I never make those decisions using this exposure data. And that's it. And I hope you enjoyed the talk.
Hi, my name is Paul Amix, and I'll be talking about developing and understanding metadata. So here we have some common questions that might come up when a user tries to work with exposure data that they've downloaded. So what is the spatial resolution of the data? What's the source of the data? What's the replacement cost? What's the data vintage? And why is this point in the river? So a lot of these are not necessarily easy to answer in a concise way. They may have multiple answers. You know, there may be nuances about the spatial resolution that need to be spelled out before a user can use it effectively. The source of the data there may be many data sources that went into creating this data set, and there's no simple answer that you can give to answer that question. And finally, the question about why is this point in the river? Exposure data is often distributed over regions in a grid and isn't intended to be used at a high level of spatial precision. But people will try to use it that way if they don't understand the limitations and assumptions that went into creating the data. So it's important to spell those limitations out so that the data can be effectively used. So what we need is a language for the science of exposure development. And as you can see, the two main goals here are to illuminate the process and acknowledge the uncertainty. So by aiming towards these goals, you'll be helping the end user of your data understand what they're working with so that they can use it effectively. So why is the metadata important for the creator of exposure data? It's not just important for the end user of the data. Good metadata can also help the creator of the data set. So you can track exact steps used to create the data so that when you're updating, you know exactly which steps to adjust and which can be reused. You know, it's often not the same people or organization that will be updating it. So as the years go on, team members may have changed. People are no longer reachable for questions. And even the organization that originally created it may have handed off responsibility to another organization. So it's important to track these steps and processes so that you know, they can be handed off to a new team that needs to do the updates. And if you've finally, if you've kept good metadata and understand exactly where things need to be updated, the expense of creating an update can be greatly reduced. You don't have to commission a whole new study to create a new data set. You may just need to update one small piece, and you can do that very effectively if you know all the steps that went into creating it in the first place. So what useful things can you find in the metadata? Typically, it's full descriptions of the mapping schemes and development patterns that were used when generating the structural distribution, the full bibliography of input data that was used for a specific country, detailed information about how each piece of data was created for the specific country or region, an explanation of how the replacement cost was determined. And beyond that, there's always the basic information that might be useful, such as, you know, descriptions of the data fields, the limitations on how the data can be meaningfully applied, and also contact information to get in touch with the team that created the data if you have questions. And here we have determining what to include in the metadata. So we're trying to answer the questions, how do we know what information is important? And how can we cut through the complexity of gathering this information? And our answer to this question has been flowcharts. So flowcharts are tools to help you determine what information should be captured. So here's an example. In this case, it's a flowchart to capture information about the work done to develop the replacement cost. So this is a process you can use to help record all of the relevant decisions and sources that went into making a data set. And it's not a rigid thing, it's a tool for you to use. So it's a tool to figure out where it would make sense to include sources and notes about the process. And since it's a tool, it's just here to help prompt you, and you can adapt it to fit your own process as needed. And here are two examples for different exposure levels. So different levels are going to need to capture different information, and they'll have different sets of flowcharts available for each level, since they're going to be, asking different questions. So on the left, we've got level 1, and that's at the global scale. And on the right, level 5 is capturing information about the precision of specific locations. So that's something to keep in mind. Make sure you're using the right flowcharts to capture information at the relevant level that you're working with. So this metadata process was designed with the ISO metadata standard in mind. So it's an international standard, and it's a standard that's currently compatible with many GIS tools. And compatibility is expected to grow as time goes on, since the standard has recently reached maturity. And at the basic level, it's an XML format that accompanies the data set. So looking back at the flowchart that we saw before, this shows the result of taking that flowchart, which is for replacement costs, and we're translating it into a section in the actual metadata XML file, shown on the left. So the section of metadata in the upper left corner describes how replacement cost was determined for this country, including sources and references. And as you can see, the actual metadata is written in paragraph form, as it's meant to be easily referenced by the users of the exposure data. And a little later on, we'll get into an actual example of how to determine, which text should go into each of these sections. Creating the metadata documents. So for actually creating this metadata, the easiest way is to use ArcGIS to produce this information. And ArcGIS can produce both the ISO metadata and the Esri metadata formats. And if you'd like, you can create both and export both of these metadata formats to reach the widest audience with your data, so that users can use whichever format works best with their software. At the time of creating the process, ArcCatalog was still in use. Nowadays, you may be using ArcGIS Pro to do this same procedure. And here are some more details about the metadata formats, and I'm not going to go into this too deeply. Just keep in mind that ArcGIS metadata is the de facto industry standard, but it's proprietary. So ISO is non-proprietary, but it's still gaining acceptance. So there's kind of a trade-off there. The last section here is describing ISO 19110. You can likely ignore this, as it's getting rolled up into the single ISO format that everybody should be using shortly. Again, this is getting into some more specific details about the process used to create the metadata files. I'm not going to go into much detail here, but please download these slides if you want to take a better look at this. And again, also the final step here is for creating that ISO 19110 format, which is the feature catalog metadata. And in the near future, that should be getting rolled up into the main ISO metadata format. So that shouldn't be necessary to take that extra step at the end. So metadata sections of note. So in the ISO metadata document, there are two categories of sections that most information will be getting put into. The lineage sections are for tracking input databases, procedures, methodologies, and data processing. So there are multiple process steps to describe each action. And this is where you'll be filling in most of the useful information about your process. The other sections that you'll be filling in are report sections, and these are used for evaluation of quality of input data, evaluation of processing methods, the final dataset quality review, and in general summaries of information about what's been produced in your dataset. So also there are multiple reports to describe each evaluation. So both the lineage sections and the report sections have the ability to include multiple steps that you can use to chunk out the information into logical groups that you're describing. Here we have some resources linked to help create your own metadata. The first link here, this is very valuable. It's the link to the flowcharts that I've been discussing. So this is the full set of flowcharts for each exposure data level, 1 through 5. So you can download that, use them as is, or adapt them to your needs if you find that you need to modify them to get what you need. The second is a document describing the metadata format in detail. So this is information about the different sections that should be filled in and where those sections actually correspond to in the ISO metadata format. Next is a document with the example metadata for the Meteor project. So you can follow along with the process for filling that information in, and that's all documented, and it describes how that metadata is being input into the metadata file. And then finally, there's a link to the Meteor exposure data. So these are the actual data sets that were produced for the Meteor project. And these will include the metadata for real data sets that you can use as reference to see how that data was created. Next, we'll be getting into a flowchart example. So we're going to quickly go through this example of the flowcharts that were used during the creation of level 3 exposure data for Nepal. So this example is just going to be touching on a subset of the categories that were used when creating the data. So we're just looking at building height, structural distribution, and the number of buildings. And I'm going to go through this fairly quickly, and the writing is small. So please download the slides if you want to look through this in greater detail. And at the end, I'll also include a link to a larger presentation about this example if you want to go into more sections and see the full process for creating this metadata. So here we have a bibliography that would be included in the metadata. Typically, we include one large bibliography, and then individual processing steps or report sections can reference this bibliography as needed. So it's included in one section and then referenced from wherever you need to. And then getting into the flowcharts, here's the building height flowchart. And as you're following along from the top, the question that's being answered here is, was data available for this country directly or inferred from neighboring countries? So was building height available directly, or was building height inferred from neighboring countries? The answer is directly. So we've taken the branch to the yes branch, the directly branch, and it goes to a box that says describe the source data for this country. So on the left, you can see what the analyst produced to answer that question about the source data. And next, we have a question that's describe the method of sampling and the number of samples for the building height. So you can see that being answered on the right. And again, please download these slides if you want to slow this down and read along as I'm describing. Next, we're going to be looking at structural distribution. So it's a new flowchart for structural distribution. And here we're answering the question of the source data description. So what is the source data description for the structural distribution? And here we have, we're answering the question, we're describing the surveys that were done and the team that collected the survey data. And apologies if my video is in the way of some of this information. As I said, please download the slide so you can read along. And then here we have, we're still looking at structural distribution, but we're looking at a separate processing step related to the site survey and with a different team performing this processing step. And here we have examples of the development patterns that were used when creating the structural distribution. So the development patterns themselves are described, as well as the process that was used to create the development patterns. Next, we're looking at the number of buildings. And so this is a new flowchart for the number of buildings. And here we're answering with a description of the source data that was used to infer the number of buildings. And then here we're answering the method that was used to extrapolate that data to a larger area. Next, we're looking at the method and sources used to infer building count from remote sensing data. And here we're answering some additional questions about inferring the number of buildings from remote sensing data and some additional sampling questions in this category as well. And finally, we're looking at answering the question of how population data was used to infer the number of buildings. To see more of the example I was just going through, you can follow the link on the top here to go to the original presentation that gives the full example with more flowcharts and fuller descriptions of what is being recorded for each particular entry. And then also associated with that, there's a link to the training materials for Nepal, and that has much more information about all of the metadata and the work that was done to create the Nepal data sets. And then next here we have more examples of actual metadata documents produced for the Meteor project. So you can follow the link to the Meteor exposure data site and download these data sets with associated metadata and get real examples of what's being recorded. So thank you for your time.
All right, now we're going to talk about equity and bias considerations that we've touched on a little bit as we've gone through, but we're going to do a deeper dive into some of these important issues. Yeah, so first of all, we're on the side of justice, right? We're trying to help people build better structures, trying to make people safer. Isn't that enough? Well, no, not really. What we're doing is using a tool set that's essentially comes from a very economic perspective. Dare I say, in its initial forms, put dollars above people. We're in a culture with, well, everybody's in a culture with a lot of history. With that history comes bias in terms of what people are counted, what is counted, accounted for in many different ways. And all of the risk analysis feeds into a larger decision-making framework, which might have problems in itself. So what we're going to do is do a deeper dive into some of these things so that we can at least be cognizant of them and do what we can. So first of all, bias in the exposure data. A lot of the basis of the exposure data is the population. And as I'm sure you know, all over the world, there are a lot of problems in census data set. It doesn't do a good job with unhoused, counting unhoused folks, undocumented folks, nomadic people. You have mass migration due to conflict or other factors. Those people are often missed, or, well, they're not in the most recent census, so they're not accounted for in other ways. Informal housing, Black, Indigenous, people of color, ethnic minorities are ignored or undercounted. We touched on this before, but that cascades throughout the data sets. And then some census data is just old, right? Sometimes it's not every 10 years. This is in the U.S., where there's been a lot of change in the country, and then that doesn't get reflected in the hazard data set. So that bias can reflect against folks that are socially vulnerable or in a position of need. So just the bias in the exposure data process itself. Census data is collected at census tracts. These can be very, very large area, and then we extrapolate them from the tracts to the grids through a process that introduces bias. On the right here, we've got 4 examples of how 4 different entities have done it, and you can see there's quite a bit of difference between them. Which is more accurate, I don't know, but that causes problems when, for example, you're trying to make a decision about how to reach out to people in Nepal after an event, for example. Any sort of problems in the extraction of building footprints, for example, if you're depending on that as part of your process, and there's and the inability to do that in some areas, that's going to cascade to your exposure data sets. And just on a very critical basis, data is better where people pay more attention, where there's more assets. More efforts are going to go into enumerating the buildings in New York City than in the Appalachian Mountains, for example. Lots of buildings aren't going to be found. But those folks might be at greater risk given certain perils. And globally, we see that as being a blind spot that needs to be considered and recognized. And next we have something that I call Adam Smith's dystopian hand. Those with less power and resources gravitate to higher risk areas, typically. Not always, but typically. So that is, the risk is reflected in the land values. And we see this consistently in the United States, where we've got flood risk. Those values are lower properties and tend to be lower income people that live there. That's reflected globally as well. And you've got folks, including this girl who's a real person who lives right there, that live in these areas that are very high risk. And it's easy when you're doing these sort of international studies to overlook the fact that these are real people and not numbers in a database. But the humanitarian effort, the aspect of it gets sort of overlooked. it's easy to ignore. But anyway, folks with less power have less ability to impact social change, or less ability to determine the outcomes of what happens when risk is identified. And risk analysis may feed into this process. So, for example, if you've got massive gentrification, that might involve clearing out areas with heavy flood risk, for example, and when that land is reclaimed, little attention is spent to address the folks that have been displaced. And in some countries, it's just quite obvious that there's a social imperative to keep quiet or you'll be cleared out. And those areas might be ones like the one that you're looking at here. Next, I want to kind of move on to some sort of structural problem that we have, and that is that all of these tools are, these risk modeling tools descend from actuarial tools, from essentially CAT models. They moved over to FEMA in the 90s, and then for the development of HAZUS, and then from that became a template for international tools that have proliferated throughout the globe to try to help make decisions with regard to risk. But that means that they consider money more than people. Now, we've tried, I think, as a discipline to extend that to social systems and also lifeline systems. But the truth is, math is hard. It's much more difficult to characterize what happens to people who are quite complicated than what happens to buildings. And believe it or not, very complicated to figure out what happens to lifeline systems that support those people. And in general, what we come up with is an assessment of how many buildings are going to be damaged and what's, how many people are living in those buildings, but what happens from there, which have a lot of factors such as social resilience, is difficult to quantify. Now, we're trying to do a better job, I think, as a discipline, but we're still not caught up there. So vulnerability is really focused on engineered construction in developed countries. So we don't have a real good idea how this amazing structure right here is going to respond to a certain excitation, because there hasn't been studies. Now, we can make some educated guesses, particularly with this one, but in general, the construction in developing countries is not as well inventoried. And just, when you think about money, you think about, well, how much does it cost to build this hut? Well, this hut, from a Western perspective, was probably free, right? Because the materials that went into it were probably collected from the surrounding area, not bought at a Home Depot. And the labor that went into it was probably community labor that was unpaid. So it's outside of the paradigm that we typically do replacement cost estimation. And one might ask, does it matter how much it costs to build this hut? If the folks that are living there don't know what a dollar is, or don't care what a dollar is, and the exchange rate might be absurd or highly fluctuable, they really want to know, and what the people that serve them as a government want to know is what they should be doing, who they should reach out to for mitigation purposes, how they should help these people understand their drought risk and the flood risk, and adapt accordingly. So keeping your eye on the ball in terms of what you're trying to produce as an answer to help, and what decisions you're trying to answer, is really critical, I think, to getting this data used in a way that's effective. An accountant's perspective sometimes gets in the way. Secondly, it focused on average annualized losses. So I've mentioned this before. Essentially, what happens is when we're trying to make decisions in terms of things that might happen, we annualize those losses and then project over a period of 50 years. What if you put the money in the bank? Would it be worth it, essentially, to spend the money now to avoid those losses, or just wait, say something happens, and then rebuild if it happens? That's a very kind of Western perspective, accountant's perspective, benefit cost analysis. But what it doesn't do is it can take into account the fact that it's the big ones that destroy entire communities that have the biggest impact on people's lives, right? Was it worth it to rebuild the levee that was protecting New Orleans? I think we can all say in hindsight that it was. But obviously, because that's a critical infrastructure that's protecting a lot of properties, you don't assess that based on average annualized loss. You assess it based on trying to prevent massive, life-changing disasters with cascading effects that affect many people's lives. And the accountant's perspective, I think, needs to be changed from the average annualized perspective to looking at the impact of some of these large, high-impact events. And lastly, the focus on average annualized losses puts the focus on areas with high frequency events, and in those areas, people tend to be more prepared. Not always, but tend to be more prepared than looking at those kind of community affecting events. So, benefit cost analysis does not help society answer the question of who. So, wealthy and highly populated cities have better risk consultants. They might be able to hire me, for example. Rural and less wealthy areas do not have tend to have the expertise to do a sophisticated benefit cost analysis. In addition, wealthier constituents have more political leverage. So if you're in Malibu, for example, you're more likely to be able to get the political power to make the changes to protect your property than folks that are living in New Orleans, for example. So here we have an example on the right where folks are living in Malibu on a hillside with a high fire risk and landslide risk in these beautiful homes. They've been mitigating their structures with walls outside of it. On the outside, whereas these folks whose livelihoods are threatened and essentially had to migrate out of their communities, did not have any such power to address a question that a problem that was really well known with the levees in New Orleans. So this is just a sort of a problem that we have. Homeowners over renters. Moving back. Equations favor conditions where a higher value property is protected. So if you're going to mitigate a high value structure, that shows that you're going to save more money than if you're mitigating structures that might be older or ending their lifespan. It's just essentially not worth it from a cost perspective. But when you're looking at who might need aid to mitigate and protect their families and who won't be able to afford to protect their own lives, for example, the equation might be flipped. So the benefit cost analysis doesn't care if you're saving if Bill Gates is we spend $1 billion to save Bill Gates $1.1 billion, which I don't think anyone would think was a good idea. The benefit cost analysis is still going to show that that's profitable or that's cost effective. So we need to sort of back up and reevaluate where the mitigation dollars are actually spent to protect us against some of these lower frequency, high consequence events that may not even be cost effective when analyzed on the dollar value, but protect the people that really need protection and cannot afford it themselves. Lastly, the process essentially benefits homeowners over renters. It asks, the recipient of these grants is going to be the homeowner, and if that's a landlord, the renter who's might have the life safety concern isn't part of that decision-making process. So more on benefit cost analysis. So benefit cost analysis is not designed to address a shifting climate. So essentially, if you've got a risk, an even risk over the next 50 years, and you're looking at whether you should spend money now or put that money in the bank, benefit cost analysis is designed to help you make that decision, right? After 50 years, are you going to say, I wish I spent that money in mitigation, or are you going to say, well, if I put that money in the bank, then I would have been able to just fix my house anyway, right? It's a very much an accountant's perspective. The problem is that's not suitable for the unique condition where benefits accrue substantially in the future, right? Where you've got, for example, a coastal risk that's getting much more severe. And it's a no-brainer that protecting against that eventual inevitability, if you will, of that coastal risk with sea level rise affecting your house, of course you would want to have spent that money to mitigate it if you can. So it's the wrong tool, I believe, to address a shifting climate. And you've got the situation where, because you're reducing the quantitative reliance on rare events, you have a situation where, from an ESG perspective, some analysts are showing that the risk from hurricane is actually going down, right? Because they're showing more destructive force in 5 events, but less destructive 1, 2, and 3 events. From an average annualized loss perspective, your risk is going down. Well, what's the problem with that? Well, categories in 1s and 2s are somewhat of a nuisance, but categories 4s and 5s, direct hits on cities, are absolutely devastating, right? It's not a matter of just the impact on property, it's the impact on people's lives. So if you have that accountant's perspective, it's really easy to make skewed decisions and take people. Building on that thought, mitigation really focuses on the decision whether to mitigate a specific property. It's cost effective to mitigate this property. You've got that grant to do that. Whereas, in fact, mitigation has significant synergy that's difficult to capture. So the sum of the parts is more than the whole, right? If you mitigate an entire community, then that community is able to survive a serious event. That has benefits to everybody in the community, right? If I mitigate my house and my house survives an event, but the community is gone, that's a drag. That's going to affect my property values. And frankly, maybe I would have, it'd be better if I didn't mitigate it because I would get the insurance money, right? So it's if you just focus on these properties, you're missing the ability to try to strengthen entire communities, as in the case of Katrina. And what we find is that vulnerable populations may not align with the evaluation of site-specific risks. So, for example, if I've got a mill town and the mill is high risk, and I live outside the mill and the mill is destroyed, my life turns upside down because I need to go get a new job or need to move, and that's not even reflected in the assessment of the risk of that side. So identifying risk and community risk really requires a comprehensive view of the entire community. So that's one of the challenges that we're facing now, when we're trying to look at ethical issues to try to protect communities. Equity issues. And the obvious example here is that the Hurricane Katrina risk breached the levees that had impacts on far away from the actual levee itself, and caused huge impacts on a community that had massive diaspora all over the country. Next, geographic precision is not accuracy. This is something that I really have to emphasize over and over. I'm a GIS guy. I know lots of GIS folks. We try to get the most accurate spatial data possible for people to make their decisions with. But building-specific data that's not based on engineered reports should not be used or publicized at the building level. I think Mike Kikuchi made that point very, very soundly. False precision leads to inappropriate decisions that really impacts people's lives and can impact property values, for example. The example here is that the Portland NAACP sued over the publication of site-specific hazard data because it was affecting property values. And in fact, that data was based on broad-scale surveys, not engineered reports. So they didn't actually reflect necessarily the housing that they had. So there's another kind of conundrum that's at the basis of all of this exposure data. Exposure data is essential to understanding risk, but the exposure data can also be used for nefarious purposes in totalitarian regimes. And exposure data, lifeline data, can also be repurposed for terrorism and for conflict. So this data has a lot of other uses. And so I think that as a community, we have to be very responsible about how we provide access to this data and how we represent it. So for an example, we've got some informal housing that we codified in a database for a client as no lateral force resisting system. That sort of obfuscates the nature of the data in a way that's appropriate for assessing vulnerability, but won't highlight that data for area that might want to clear out such type of housing or have other nefarious purposes. And I think that this is very important when we start to think about lifeline data sets, particularly that might have very vulnerable assets that we don't want to put out there in a way that's used for nefarious purposes. So that's a lot. And you may be asking, well, what am I supposed to do about that? Thanks very much. You're just trying to teach me how to put these data sets together. Well, I think that it's important to have a sophisticated understanding of these problems as you embark on your sort of risk analyst journey for wherever that you may sit, so that you can help discuss these, spot these issues at the pixel level, the GIS level as they come up, and that you can sort of represent them as you represent the results of this analysis. My feeling is that, this is a conversation that we're all trying to have on these processes, and being aware of them is the first step. What else can you do? Help contribute to more sophisticated research in this area. There's a lot of research to be done here. And my hope is that as more money goes into looking at the impacts of climate change, that the disasters area will become more sophisticated and start to focus on people over dollars, for example. Encourage transparency in the process, but not always openness in the data. Be very, very clear about the limitations of what you do. But also protect that building exposure data so that you can make sure that it's used for appropriate purposes and protecting the people that it represents. You got to protect people's privacy. You don't want any personal identifiable information out there, and you don't want to insinuate that you understand buildings at the building level when you, in fact, have not put the effort into understanding them. Acknowledge the uncertainty, and if your data sets are too uncertain, aggregate them up for the analysis or after the analysis has been done. Speak up about the limitations and the issues and how this data is being used at your organizations. And really, I think, focus on the questions that you're trying to answer, and that is the needs of the people that we're ultimately all trying to help protect and make more resilient. And that is largely often to find the accidents waiting to happen.
Hello, and thank you so much for joining us. We're going to present a case study on assessing climate change impacts with building exposure data in Antigua and Barbuda. So before we start talking about the modeling process and all those details, we're going to give a little bit of background. So we already talked about climate change adaptation. But now we're going to introduce the concept of the National Adaptation Plans as defined by the United Nations Framework Convention on Climate Change, known as the UNFCCC. So the objectives of the National Adaptation Plan process, it is important, we're going to say a little bit more next, but this is a process. The objectives are to reduce vulnerability to the impacts of climate change by building adaptive capacity and resilience, and also to facilitate the integration of climate change adaptation into relevant new and existing policies, programs, and activities at all levels. So we mentioned the National Adaptation Plan is actually a process. We call the NAP process. This is a table that I got from the technical guidelines for the NAP. You have a link here. I invite you to go and check them out. They're very interesting, and it's important for you to learn more about this process that has different elements. Today we're going to focus with this presentation on more on the technical part, on element B, preparatory elements, where we have these four main steps that we will review. So the first one is analyzing current climate and future climate change scenarios and risks. Second step, assessing climate vulnerabilities. And then we will see the third and fourth steps, identifying adaptation options and reviewing and appraising those options. So let's start with the first step. Analyze current climate and future climate change scenarios and risks. What we will see in this part are results of a project that we did with other partners for the Department of Environment for the government of Antigua and Barbuda. This was called the Climate Change Risk Modeling Project for Antigua and Barbuda, where we produced different types of outputs. We analyzed climate hazards and then climate risks. So now we're going to talk about climate change risk modeling. So up to now, what we have seen in introduction and also some examples, we talked about risk modeling under current climate. So what's interesting about this is how we're going to modify this approach to include a changing climate. So let's start with the current climate just to do a refresher. We talked about the need for information on the hazard, the exposure, and the vulnerability. So for example, let's take in this case, hurricane, wind, and surge. So we need information on both of these hazards. We need information on exposure, for example, buildings, and then information on the vulnerability of these buildings to both wind and flooding. With this information, we are able to estimate different types of losses. As you can see here on the screen, it can be direct losses, can be also, we can have models to estimate downtime based on these direct losses, and also we can have results for different type of industries if we want to do some kind of sectoral analysis. So this is for the current climate. Let's say here it says 2020, it can be 2023. So how do we change this? How do we change the model? So what we call this change is actually climate conditioning of the risk model or CAT model. So what we do is we modify the hazard. For example, it can be the wind or it can be the storm surge based on different climate scenarios. In this case, we use the IPCC, the Intergovernmental Panel on Climate Change Scenarios, the ones that were defined before the RCP, so Representative Concentration Pathway 4.5 and 8.5. So what we call the stabilization scenario and a high emission scenarios. There are new climate scenarios, but we can also use those, but it's the same concept. The important thing here is for you to understand what is the process. So we start by climate conditioning the hazard. What does this mean? So we know, based on different types of projections, based on these different climate scenarios, how the wind, how the hurricanes are going to be affected by climate change. So we expect, for example, higher winds, so we can in this way modify the hazard. Also, we expect higher temperatures in the sea surface temperature. So that means besides higher winds, it also means higher waves. And the same goes with sea level rise. That also affects the height of the waves and the severity of the flooding. So based on these scenarios, we can make estimates on the changes on the hazard and then run again our risk model to estimate the losses again. But this time we can do that looking at the future. We can do that, for example, for the year 2030, we can look at 2040, 2050, and so on until the end of the century. And this is very important because it allows us to understand, to estimate how the impacts, how the risk is going to change through time. And this we will see is very important for planning, to know what we can expect. And so using this approach, we can estimate the losses again for different decades, different climate scenarios. And also what we did was looking at the exposure to sea level rise and nuisance flooding. We will give some examples of that next. So let's talk about the exposure development process. We collected almost 100 GIS layers, which included very detailed LiDAR data, building footprints, valuation from parcel level data, data on essential facilities, we will give some examples, also on utilities. So using the LiDAR data, we were able to get a detailed elevation model. This digital surface model that you can see here in the image was used to be able to estimate the height of each of these buildings, and then from that get a number of stories or floors. Something very important of exposure development is to be able to locate critical facilities. For example, we can have medical offices, clinics, hospitals, schools, police, different type of utilities, government, port facilities, hotels and resorts. In this case, when we're talking about islands and we're talking about touristic destinations, hotels and resorts are very important for the economy. So it's very important for us when we want to develop exposure to understand which are the types of facilities that we want to locate, depending also on our analysis. So this is what the final product looked like on building exposure. We got this grid where we have replacement cost in $1 million, and also we can have different values, number of buildings, the total area of those buildings, and the total replacement value by administrative unit. So these are some of the results from the risk modeling analysis. This is, for example, the average annual loss for hurricane, and we have different losses. For example, the graph on the left, top left, it's losses from storm surge. We have the same for storm wind, and then we can also do a similar graph, but normalized by the exposure. So this one is in, for example, losses per $1,000 of exposed buildings. And we can see we have different colors. The colors indicate the type of climate scenario. We can see how these average losses grow through time. So this is because of what we have been talking about on climate conditioning and how the climate models project that hurricanes will get stronger, winds are going to be stronger, storm surge, the sea level rise will make the sea go up and also get higher waves. So we're expecting more losses over time. And then we can have the same results, but in a graphical format. We can also produce results for different types of event, different return periods, or probability of occurrence. So for example, this is for a hurricane of 100-year return period, or what we call a 100-year event. And we can see here we have similar graphs and similar maps. Other very useful and important results that we can produce are those maps related to sea level rise and nuisance flooding, which is the flooding that has a 10% probability of occurrence in a given year. So what you see in different colors are the areas that are expected to be flooded in different decades. These kinds of maps are important because we can see areas where we expect to have different problems, can be now or can be in the future. So for example, we can see areas where we can have accessibility issues, where roads are expected to be flooded frequently, or areas where resorts can suffer the same. Areas where, like the port, can suffer disruption due to this frequent flooding. Also, a similar type of analysis we could do looking at, for example, wind damage. So now we're moving on to step 2, assessing climate vulnerabilities. So what you can see on the right is one possible framework that we can use to assess climate vulnerabilities. But before we go into the details, we want to mention why are we assessing vulnerabilities. So the aim of the vulnerability assessment is to understand what type of adaptation measures we can take to reduce these vulnerabilities, to reduce potential or avoid potential impacts, and also create more adaptive capacity. We'll talk more about this. But it's very important to understand what's the aim of this analysis. So we can see on this framework the main elements of vulnerability are potential impact and adaptive capacity. And at the same time, to be able to assess potential impacts, we need to understand exposure and sensitivity. So we have been talking about this, or we talked about this during the introduction, where we talked about how different disciplines, the disaster risk reduction and the climate change community, have different terms and definitions. So in this case, we are talking about vulnerability in the context of climate change. So we're using the definition that you can see here on the left. The degree to which a system is susceptible to or unable to cope with the adverse effects of climate change. So it's very important that it's not just sensitivity or potential impacts that can be suffered from climate hazards, but it's also the adaptive capacity, the capacity that a system has to adjust to climate change to moderate potential damages. Then how do we define potential impact? The potential impact are the potential negative effects on a system, population, or asset based on its exposure and sensitivity to a climate hazard. So if we talk about sensitivity is more closer to the definition of vulnerability that we have seen for disaster risk reduction, for CAT modeling, which is the degree to which a species, natural system, or community, government, or other systems would be affected by exposure to a changing climate. And again, exposure is the presence of people, infrastructure, natural systems, and economic, cultural, and social resources in areas that are subject to climate hazards. So this all means that in order to assess the vulnerabilities, we need to assess what is the potential impact and also assess what is the adaptive capacity of our system. Can be an asset, can be a sector, people. What is the adaptive capacity to respond to each of these impacts? important aspect of this process is to be able to score vulnerabilities. And this is useful because it allows us to prioritize those vulnerabilities that are more important, and also in the end this will be useful for defining adaptation measures. We can see which vulnerabilities require most attention. So in order to do that, we mentioned already about the framework and how vulnerability is defined by combining potential impacts with the adaptive capacity of the system that we're looking at, or the asset that we're looking at, for to each of these potential impacts. So what we do is to score, on the one hand, the potential impact, and also to score, on the other hand, the adaptive capacity to that impact. And here we have on the left a table. You can see this was adapted from the California Adaptation Planning Guide. You have the link. I invite you to go and take a look, and you can get more information about this framework. And we can see that in this case it's a qualitative scale from low, medium, and high. Also, we can have different levels. We can adapt this scale as we see fit, and depending on the project that we're doing. But we, in this case, have these 3 levels. And for example, if we look at potential impact, we see that in the case of scoring of low, impact is unlikely based on projected climate hazards and will result in minor consequences to the sector. On the other hand, on the other extreme, we have high potential impact, where impact is highly likely based on projected climate hazards and will result in substantial consequences to the sector or system that we are analyzing. A similar way we can use the adaptive capacity when we talk about low adaptive capacity, and the population, organization, or asset lacks capacity to manage climate impact. And this means that major changes will be required to increase this adaptive capacity. On the other extreme, if adaptive capacity is high, then our system that we're looking at, or asset, has high capacity to manage climate impact. So once we rank this low, medium, and high, we can assign a 1, 2, 3 score. And as you can see here on the right, this is a matrix that we can use to combine potential impacts and adaptive capacity. Again, we can have more levels if we want it, but basically you can see if the potential impact is high and the adaptive capacity is low, we expect the highest score for the vulnerability. So it's a 5. In the other extreme would be potential impacts being low and adaptive capacity being high, and we can see we get a score of 1. So what kind of data can we use to do this vulnerability assessment? So of course, what we have seen the results of the risk modeling. We will show some maps, and we have seen also very useful both maps and graphs. We can use that to understand potential impacts. So that is one source. Another very, very important source is stakeholder consultations. And having different types of stakeholder consultations during this planning process is very important. It's supposed to be a participatory process, which is not only helpful because we can collect useful information, as we will see, but it's also important to be able to share the results, to be able to hear people's opinion, and for them to have an input on our plan, both in determining potential impacts and understanding their vulnerabilities, what are their capacities. That's very important to hear from them, but also understanding what are their priorities, what they think are ways to better prioritize adaptation measures, what they think works, what we should be doing. So it's very important to have stakeholder consultation throughout all the process. So we will see this as a very valuable source. Because of course we cannot model everything. Our models are limited. Also, we don't have resources to model everything, every sector, every impact. So it's very important to hear from the people. And also sometimes we find out that there are things that we didn't think about, and that, as I think Georgiana mentioned in her presentation, the community knows best. So this is a very valuable source that we should not underestimate. And then other potential sources are, for example, reports on past events or the media, or also reports on current status, other projects that can give us ideas on the current adaptive capacity of the sector or the asset or system that we are studying. So that's also very important. And they do say that the past is not a good reference for the future, but sometimes we do discover past the impacts that maybe we do not think about, and also can give us some ideas on their current susceptibility, and as I was saying, current adaptive capacity. So we start by looking at the climate hazards that are important for our study area, which can be hurricane, severe wind and higher surge, can be sea level rise, extreme heat, and drought. And also, of course, we're looking at climate projections of these hazards, so how these hazards are going to change through time. There are different ways in which we can organize the vulnerability assessment other than looking at the different hazards. Also, what we can do is to look at different thematic areas. So we look at hazards and then different themes. For example, we can look at buildings, we can look at lifelines and critical infrastructure. We can also look at the supply chains. Depending on the sector that we are analyzing, also the type of economy, we may be interested in understanding impacts to supply chain. And then also another area could be economic, where we look at more macroeconomic impacts that may not relate to any of those other sectors, but are more affecting more generally the society. So now let's look at some examples. This is an example of a vulnerability for hurricanes and thematic area buildings, and it reads, certain commercial buildings in Antigua and Barbuda are likely to be damaged by wind from hurricanes, and impacts are projected to become more severe by 2050. It's very important that when we state the vulnerabilities and we describe them, we do it in a layman terms, in an easy way for everyone to understand. And in this case, we assigned a vulnerability score of 5 that in our ranking was the highest. And this score is based on the combination of the potential impact and the adaptive capacity. So as I mentioned before in the framework, that is the way that we define vulnerabilities, combining both. So for this kind of analysis, we can use the maps that we developed, the climate risk maps, where we can see projected losses, for example, for different types of events, for different decades, and we can see which buildings and how many, or which sector we're interested in looking at, which facilities, etc. We can see that those are expected to be damaged or not, and then characterize our vulnerabilities this way. In this case, we were looking at certain commercial buildings, but we can look at whatever industry we want. So here we have some examples on vulnerabilities related to supply chain. For example, related to hurricane, one vulnerability reads, hurricanes directly impacting Antigua and Barbuda cause disruptions to supply chains due to impacts on shipping operations which affect trade. But also something that we discovered was that hurricanes that were impacting overseas suppliers, for example, suppliers in Florida, also cause disruptions to supply chains in the Caribbean. Also, I wanted to mention this when we talked about using data from consultations. So this is an example on the left on Mentimeter. So this is a polling system that you can use to get feedback from stakeholders, and we asked them about impacts, about their vulnerabilities, and this one on supply chain emerged as a very high one. From 1 to 5, it got almost a 5. So you can see here it got a 5 in vulnerability score. Similarly, we looked at sea level rise and how sea level rise can affect port. So in this case, what is needed, I'm going a little bit ahead here, but this is a high level assessment. So we saw, based on the sea level rise and nuisance flooding, that there could be port disruption. But then a more detailed study can tell us more about this risk. So here we have some examples related to sea level rise. Under sea level rise projections, beach will be lost to sea and erosion is expected to accelerate. This phenomenon directly affects the profitability of the tourism sector and may indirectly affect commercial businesses. So in this case, we were looking at impacts to commercial businesses, but likewise, we can see we could estimate impacts to tourism or to other sectors, for example. And this was considered an economic vulnerability because it was an indirect effect. So it's the commercial sector being affected because the tourism sector got affected first. Also, regarding sea level rise, we can look at critical infrastructure and impacts on critical infrastructure. So as we mentioned previously, there are some areas where we can have accessibility issues during floods. And this is going to get worse as decades pass due to climate change. So we can also individuate problematic areas where we should focus with our adaptation measures. So once we defined the different vulnerabilities and we were able to score them, we are going to identify adaptation actions. Here are 4 key areas that we propose. One is physical adaptation and policy planning. We'll see some examples. One is about climate proofing buildings. Another one on financing and financial instruments for adaptation. And last, one related to training, capacity building, and knowledge transfer for climate change adaptation. And if we're looking at the commercial sector or businesses, it's also very important to focus on business continuity planning. So here we're going to give some examples on the different actions that could be identified and also how they can be reviewed. So, for example, when we talk about the area of physical adaptation and policy, we look at things like building code enforcement, building retrofit programs, zoning and land use planning, and also, for example, if we're talking about heat, encouraging, incentivizing the use of pervious and climate-smart surfaces in new development. And there are different ways in which we can assess or review these or appraise these measures. So as I was saying, it's very important to ask the stakeholders that are involved for their input. So one way to rank them, or one of the inputs that can be used, is from stakeholder consultations. And then something else that we can do is to also look at other criteria that this can help us to either rank or to organize the way that we're going to implement these measures in the future. So we first need to identify those measures and rank them based on importance, and then we need to do an implementation plan. And that's beyond the scope of this presentation. But something what we can do, for example, is looking at the co-benefit of each of these measures, which means if we're, for example, talking about a specific sector, thinking about whether there are benefits to other sectors of implementing this kind of measures, or other types of benefits that are not directly related to the measure we're implementing. Then we can also have some relative estimate of the cost. We can have a specific estimate in dollars, ideally, but if not, we can have some relative scale like the one we used here. And also something very important to consider is the time frame of implementation. So whether it's a measure that can be implemented in the short term, if it's a medium or long term measure. For example, when we're talking about zoning and land use planning, generally it's a long time frame. So other area that we mentioned was climate proofing buildings. So here we focus on the building itself. For example, using hurricane shutters to cover openings. So in this way, the wind will not get in, and then it will be less effective. Also, we can look at, if we're talking about heat, increasing the presence of cool roofs, cool walls, using water membranes if houses or buildings do not have them, to prevent roof leakage from flooding, from rainfall, for example. Installing barriers to keep flood waters out of the building. And we can also do a similar assessment on the co-benefits, costs, and time frame. There are many different financing and financial instruments that we can implement, and this will depend on the sector we are looking at. If we are, for example, looking at businesses, commercial businesses, if we're looking at the society as a whole, or if we're looking at a specific vulnerable group, if we're looking at agricultures, etc., there are different instruments that will apply. So here we just have some examples, like working with the insurance sector to introduce climate change related microinsurance schemes, improving access to finance after disasters. Something very important is strengthening dialogue between insurers and policymakers around Build Back Better. So this is important because sometimes after a disaster, maybe people that were affected get money back from the insurance company, but rebuild their house the same way. So it's important that we can include adaptation in this kind of building to rebuilding to build back better. Then when we talk about training, capacity building, and knowledge transfer, we, for example, can develop and deliver education and training resources. We can increase access to business-related emergency preparedness and mitigation resources. This will be important, for example, for commercial sector. We talked about supply chain, so supply chain management is also an area very important that can emerge depending on the vulnerabilities that we find in our analysis. So identifying, for example, alternative suppliers, having an off-site inventory of goods, and having also scenario planning. And something that can be helpful is creating a compendium of climate change adaptation practices.
All right, so hopefully you've gotten a good idea over the last few days on the development of building exposure data, how you can use EO in that context, what some of the limitations are, what to watch out for, and so on. We're going to leave you with some thoughts on future directions, things that are coming down the pike. As with all things, AI is making a pretty big impact on the development of exposure data. AI can be used to kind of interpolate through the gaps, a smarter method of interpolation spatially. If there's things that aren't necessarily codified in the EO data and you don't have a basis for making an educated guess. So we're going to go through a demonstration of that in a minute here. And also we're seeing a lot more detailed in situ data. Street view, UAV data is a great way to supplement your database, your mapping schemes, and so on. We will always use street view data. You have to be careful that you don't bias the data based on where that street view data has been collected. But a lot of folks, I think the World Bank is working on trying to extract attributes directly from this type of street view data on a frame-by-frame basis so that they can attribute specific things to on a building-by-building level. This is a great way to get a pretty detailed survey of a given city or area without having to deploy resources. UAV is kind of same thing. You don't have that ground view, but one thing that's being done with UAVs that's quite exciting at OSM, for example, is the extraction of detailed elevation data, which is required for good flood modeling. This is something that they're talking about crowdsourcing, and a great opportunity to do some capacity building as well. So this is an example from some economic modeling software that we're putting together, the extraction of where computer tech hardware is made throughout China, and we're calling it the production capacity of a given cell. We have methods that we're pretty solid on in terms of figuring out where in an area there's the ability to produce things, but to try to figure out where computer tech hardware is made as opposed to mining in an area is quite difficult if you don't have in situ data statistics to help you model that. But AI has proved very valuable as a way of quickly generating these types of surfaces. Here you'll notice that computer tech hardware is estimated to be outside of major urban areas, but not all urban areas. So where you've got clusters of production capacity. So this is a good way to overlay this with hazard information to figure out where you've got the potential for supply chain disruption. And the corollary here is if you look at mining, here we have high levels of mining kind of limited to quite mountainous areas or certain areas that are rich in minerals. If you're dividing that kind of evenly throughout the space of production capacity and industrial operations in general, then you miss looking at what might be a disruption due to certain things that are required in pharmaceutical manufacturing or what have you. So this gives you a better way of tracing the cascading impacts of supply chain disruption, and we're able to do that based on using AI to subset and basically interpolate a finer resolution of the production capacity. And I think that there's a lot of applications like this that people are looking at. But with any advanced technologies, there's upsides and downsides. AI can be used, can introduce bias, particularly if the training data sets are biased that you're using. Also, it's just going to give you the general thrust of things. It's not going to highlight exceptions. So and sometimes it's the exceptions that you're most worried about. For example, if you go back to the example of trying to find rural areas that might be impacted by the Nepal earthquake, if AI didn't have any of those population data sets to begin with to train on, then those would be missing. And in fact, those are can be the areas that you're most concentrated on reaching out to. And the detailed use of in situ data can also aggravate privacy and security concerns. So that's, I think, kind of obvious, but as we start to get more sort of person-specific information, then we need to make sure that people's civil liberties are protected as well.
Thank you very much, Charlie. and it was great to hear about the future directions. So let's briefly summarize part 3 here. We looked at exposure data best practices, developing and understanding metadata, equity and bias considerations, and we had another case study, this one involving assessing climate change impacts with building exposure data in Antigua and Barbuda. So let's review what we did here in this 3-part training over the last week. In part 1, we talked about the development of regional exposure data with Earth observations, the basic process of developing that data, structural mapping scheme development, and some case studies involved with Tunisia. In part 2, we talked a little bit more about site-specific exposure data, and we had some case studies on developing building level exposure data sets in New York State using HAZUS flood data. We looked at using Earth observations to develop building structure data sets, and then another case study on sampling from street view to characterize vulnerability. And we hope that the techniques demonstrated in those case studies can be taken back home and applied with local data in your regions. Then in part 3, we talked about assessing utility and communicating uncertainty, specifically on communicating metadata, best practices, and equity and bias considerations. With all this, we hope that in the end, you are able to walk away from this training with the ability to recognize what building vulnerability is and why it's important for risk modeling, to identify the core elements of natural hazard risk modeling and asset loss estimation, the ability to apply a basic procedure to model built infrastructure exposure and vulnerability using Earth observation data, to apply approaches to validate building data with imagery for regional data sets, and then to apply strategies to identify and address equity and bias considerations. Charlie did a great job of summing up the future directions of this work. Our work is not done, so please look for similar trainings on climate and disaster risk in the future with the aid of Earth observations. Just as a reminder, there's one homework assignment. These are a Google form submission. It is open today, October 10th, 2023, and will be due 2 weeks, so October 24th. And all these can be accessed through the training webpage. A certificate of completion will be awarded to those who attend all 3 live parts of the webinar series, complete the homework assignment by the 24th. And if you do so, you'll receive a certificate of completion via an email approximately 2 months after the completion of this course. Here's the contact information for Charlie, Paul, Mike, and Mariana, along with links to the training webpage where we've posted all the presentations. We'll get the Q&A documents cleaned up for accuracy and post those as well as the training videos. We'd like to take a moment and acknowledge those that help make this training possible. First is the NASA Applied Sciences Disasters Program and the award for the NASA grant listed here. NASA Program Manager Shana McLean, the UK Space Agency, the British Geological Survey and the Meteor Project, the Global Facility for Disaster Reduction and Recovery, National Society of Earthquake Technology in Nepal, the Antigua and Barbuda government, the United Republic of Tanzania, USAID, Miyamoto International, OpenStreetMap, Keith Porter of SPA, and the Global Earthquake Model. We'd also like to thank Robert Chen, the director of CESIN, the Center for International Earth Science Information Network, Caroline Holtquist from the University of Canterbury, and Yuri Gorokovich, Professor, Earth and Environmental Sciences, the City University of New York. So I'm sure there's a lot to talk about, so let's just dive right into the question and answer session. Okay, thank you very much. Question 1, are engineering reviews mandatory?
I'll take that, Brock. So when we develop these exposure databases, you want an engineering review to characterize those risks. You know, the nuances are in the details. Really depend on the hazard, what your exposure is going to look like. So, you know, if we're looking at hurricane, we'll be looking at much different things. You know, hurricane resistant components, straps, impact resistant stores, things like that, compared to, you know, a much different hazard such as seismic or flood. When we do those on-site engineering reviews, it's definitely required an engineering review, mainly for due diligence purposes.
Great, thank you. It looks like the second one here was from your content in the beginning of the presentation.
Right.
Yeah, feel free to mention about rolling up a portfolio.
Yeah, so, you know, we say here, you know, it depends on the application. If we're looking at a, you know, a single event, we can just pretty much add up losses for these individual properties. But if, you know, if the application is insurance, I think what they're talking about, we run these properties through an event set. So we apply certain things such as deductible, and from there we begin the application process.
Great, thank you. And question 3, how can we apply this metadata to study sea level change?
So I'll take this one. I got some help from my colleague Georgiana Esquivias answering this. So the flowcharts that were created were examples for tracking and developing a building exposure, which could be used for understanding the number of buildings and people that are vulnerable to sea level rise. And as I mentioned, those flowcharts can be augmented and built upon by individual users to help them structure their study and create steps for answering the study's questions. So the metadata can be used for documenting the data sources, the bibliography, the lineage, and the processing steps of the sea level data analysis. And this is important for users to understand the specific data sources and the elements of those data sources, and the specific SSP and RCP scenarios that were used in the study. And an example of using this, applying this to sea level change, would be the developing a community database from building footprint and building attributes. And then from there, the user could assign the first floor elevation and begin to assess the likelihood of loss given annual nuisance flooding, storm surge, and expected sea level rise.
Great, thank you. And thank you, Georgiana, for chiming in on that as well. Question 4, is there bias in the various location risks too? And it looks like this may have something to do with Charlie's presentation. If location risks mean hazards, yes. There is uncertainty about the many natural hazards, and science is constantly updating assessments of risk, particularly considering climate change. If location risks mean site-specific risks, also yes. There can be many bias in site-specific risks. The classic example is undervaluation in tax assessor data, but also maybe there when a proxy is used for rigorous assessments, such as assuming vulnerability from year builds. So hopefully that gets to the heart of the question that was asked. Question 5, is risk modeling incorporated into many official city plans worldwide? Yeah, sovereign nations, states, and cities at risk internationally are beginning to model risks to understand the impacts of climate change, and is being encouraged by the Sendai framework and sustainable development goals, and accordingly the UN, the World Bank, and others. Of course, uptake varies substantially, and sharing knowledge is critical. Pretty nice that we're having this training here. So a way of sharing this knowledge. I think we can all learn from each other as well. That's why these types of training opportunities are so important. Much more is needed to be done. Policy is lagging. Cities are not making the hard decisions necessary to implement changes based on risk, especially evolving risk. With 50% of the population living in cities, Yes, this is sort of where the rubber hits the road, so to speak. Question 6, there should be a beneficial metric for life. And the answer to that, this is done, but it's quite controversial. Life safety absolutely is a factor. Question 7, is the susceptibility analysis that you did for calculating building exposure, is it the susceptibility analysis that you did for calculating building exposure? And construction type classifications of the general residential building stock was available through the population and housing census. We reviewed these material types and construction classes in parallel with the relevant building code and ground imagery using Google Street View or Mapillary. Online ground photos to assess and assign vulnerabilities to each unique building type. A review of preliminary damage assessment, Hurricane Irma, was also reviewed to assess regional construction practices and common deficiencies prevalent in regards to hurricane wind. Here on the case study for Antigua and Barbuda, how did you calculate the replacement cost for the different types of buildings? So the creation of unique building patterns, development patterns, and their associated mapping schemes allowed us to both identify unique structural types, building materials, building footprint sizes, and number of stories. Through discussion with local experts, we assigned an average replacement cost per square meter for each model building type and aggregated the results up. So hopefully that a little bit more explanation of that method can clear that up for you. Thank you very much. Question 9. In assessing the vulnerability, why will you use vulnerability scoring over index-based approaches like the Social Vulnerability Index and Adaptive Capacity Index?
Brock, I can respond to this one if you want.
Oh yeah, please.
Okay. So there are many approaches that you can take. If you look at the UNFCCC guidelines, there are examples there, but also if you look at plans, I think there's one approach per plan. So we just developed this one based on the context, on the guidelines, on the fact that we're in the Caribbean. So we looked also at some frameworks that were developed in the area. We also find that the California Climate Adaptation Guide in this case was useful. And also something that sometimes it's important is that the countries in the end sometimes are, your clients, and sometimes they have their own requirements. So you respond to a tender or you work with them. And in this case, they wanted to have a ranking on the vulnerabilities with a scoring system. So we find that this was a good approach, but there are many that you can take in this as well. And some important thing is that besides adaptive capacity or social vulnerability that can be considered as well, you need to understand what are the potential impacts. So regardless on the approach, you need to see what's the definition of vulnerability and what are the components, and make sure that you're considering all the different aspects.
Great, thank you very much.
Thank you.
And question 10. Are there any figures for various impacts regarding code black cleanup? And there are models for bomb impact looking at things like human threats, basically impact given radius from the device. This is not work that we do, but the same types of databases are used, just different vulnerability assignments. Cost of cleanup is similar to other debris challenges such as hurricanes, unless radiation is an issue. Others have looked at hazards and modelified the damage functions to account for blasts. An interesting question. Thank you for asking that. Question 11, how long did it take to develop the exposure data sets in the Antigua and Barbuda case? And what was the size of the island studied? Oh yeah, great question for those who would like to do this in their work and try and estimate the time to pull all this together. And it seems like it's about a period of 6 months. They're quite small islands, a few hundred square miles. So hopefully that gives you an idea of scope. Generally, putting together a detailed level 5 data set for Antigua, we ran into the many same issues that we have for looking at a much wider or more populated areas such as New York City or Los Angeles County. Because coastal issues were key, we wanted to drill down to that higher level of resolution. Barbuda was a far greater challenge than Antigua because of the lack of data and the relatively recent hurricane damage. These are all great questions. I think we're going to end this now. We're at the top of the hour. I would like to say that within the week, we're going to have a survey out. Please consider filling that out. We try not to make them too long, and we really do use this information to help us guide what we're going to train on in the future. So please let us know about your needs. I'd like to thank everybody who contributed to this training. It was a great experience. We have one more later today in Spanish.
No, yeah, thanks everyone for joining. And if you have any specific questions, the emails are all up here, so feel free to email any of us and we'll get back to you. Thanks again, Brock.
Thanks, everybody.
Yes, same. You can email me and with more questions if you have on Antigua and Bermuda. Thank you.
Thank you for making yourselves available to the questions from the participants. We had over 600, almost 700 people attend this training over the last week. That show there's a lot of interest, and rightly so, for this type of work. So please look for future trainings as, like I said, we're not done addressing this issue and trying to put the power of Earth observations and the work by teams such as this to help save lives. So thank you very much, everybody, and enjoy the rest of your afternoon or day. Stay safe out there. Appreciate it.